Molecules are formed when elements are combined. The atoms in molecules are held close together by attractions called chemical bonds. Forming a bond releases energy. We determine a bond's strength by measuring how much energy is required to break it. There are many kinds of chemical bonds, and each has its own range of strengths. We'll cover the ones that are critical for the formation and operation of living matter: covalent, hydrogen, ionic, and van der Waals. Covalent bonds involve the sharing of a pair of electrons by two atoms. Here we have two hydrogen atoms approaching each other. If they get close enough for their electron shells to overlap, they will begin to share their electrons. Each hydrogen atom is now associated with two electrons in what amounts to a completed valence shell. The covalent bond has transformed the two hydrogen atoms into one hydrogen molecule. Its formula is written H2. This is a single bond because it is created by the sharing of a single electron. There are a number of ways to illustrate a molecule. One is called the structural formula. It focuses on the bond holding them together. Here, the single line indicates a single bond. Another, called the space-filling model, focuses on the shape of the combined atoms. And another, called the ball and stick model, is good for medium-sized molecules. The hydrogen molecule's bond strength is 4.52 electron volts. An electron volt is the energy acquired by a single electron when it is accelerated through a potential difference of 1 volt. Here's the oxygen molecule. It contains two oxygen atoms and is sharing two valence electrons and is therefore a double bond. Its bond strength of 5.13 electron volts is stronger than a single bond. Here we have one oxygen and two hydrogen atoms coming together to form a water molecule, H2O. They are joined by two single bonds. And here we have methane forming from a carbon atom and four hydrogen atoms. Of all elements, carbon is unparalleled in its ability to form the large, complex, and varied molecules needed for life. This is because it has four valence electrons. Carbon atoms represent a significant percentage of all living organisms. That's why any material containing carbon is called organic. Each of the four bonds has a strength of 4.3 electron volts, for a total strength of 17.2 electron volts. The attraction of an atom for the electrons of a covalent bond is called electronegativity. The more electronegative an atom is, the more strongly it pulls shared electrons towards itself. In a covalent bond between two atoms with the same electronegativity, the electrons are shared equally. This is called a nonpolar covalent bond. Hydrogen and oxygen molecules are examples. When an atom is bonded to a more electronegative atom, the electrons are not shared equally. This type of bond is called a polar covalent bond. Water is an excellent example of this. In covalent bonds between oxygen and hydrogen, the electrons spend more time near the oxygen nucleus than they do near the hydrogen nucleuses. Because the electrons have a negative charge, this creates a region of partially negative charge, and it leaves the regions around the hydrogen atoms with a partially positive charge. Polar covalent bonds, in turn, enable additional molecular bonding called hydrogen bonds. We'll continue to use water as an example. The relatively positive charged hydrogen atoms in one water molecule are attracted to the relatively negative charged oxygen atoms in other water molecules. Water-hydrogen bonds are strong because oxygen has the largest electronegativity. Yet it's only about 1/20th as strong as a covalent bond. It's the hydrogen bonds between water molecules that have to be broken in order to turn liquid water into gas. We'll see later that it's hydrogen bonds that hold DNA strands together. Sometimes, two atoms are so unequal in their electronegativity that one strips a valence electron from the other. Sodium and chlorine are a good example of this. The transfer of an electron leaves one with a net negative charge and the other with a net positive charge. Atoms with one too many or one too few electrons are called ions. When two ions with opposite charges come close together, they form a bond called an ionic bond. Once the sodium atom loses the single electron in its third shell, it is left with only two shells. Its new valence shell is complete. It now has a net positive charge. The chlorine atom has completed its valence shell and now has a net negative charge. The ionic bond has transformed the two atoms into sodium chloride, salt. Van der Waals interactions are named after the Dutch physicist who developed the equations for the behavior of molecules in gases and liquids in 1873. We'll use two molecular oxygen molecules to illustrate how the force works. Most of the time, the negative charge around a molecule's nucleus is uniform. No force exists between the two molecules. But because electrons follow the laws of quantum mechanics, their positions can change over short periods of time. If they were to group on one side of the molecule, that side would appear negatively charged relative to the nearby molecule. And because like charges repel, it would tend to push the electrons in the other molecule back. This in turn creates a situation where the molecule on the left is relatively less negative, or equivalently, relatively more positive. And because opposite charges attract, we get a very weak and temporary attraction between the two molecules. This is the van der Waals force, and its strength increases as the number of electrons in the atoms, or the number of atoms in the molecules increases. These forces are ubiquitous in nature and influence the structure, stability, dynamics, and function of molecules throughout physics, chemistry, and biology. When comparing the strength of these bonds, we find that ionic bonds are the strongest, followed closely by covalent bonds. Hydrogen bonds are significantly weaker, and van der Waals bonds are the weakest.